第10章，第10章可能看一下吧。如果我觉得礼拜五我们应该可以教一点点，可能就考个非常简单的部分吧。然后我想想看，第10章，对，第9章、第10章会有一些没有写完的作业嘛？那我们还是让子静把题目跟解答放上来，然后大家可以稍微看一下。Okay. Okay. Yeah. Let's start with the organization thing again. So for people who haven't been here, yeah. So we are on the last week of teaching now, and so we need to think about finals and last homework. And because we forgot to give you a homework problem set last week, so we will handle all the last problem set today, and we'll do next Tuesday. That will be like the first two problems in chapter 9. Actually, let me just try this if I go really quick all the way. Yeah. Shit. No, that's very bad. Doesn't work. Can I do this? This and okay. But what about OBS? Okay, OBS is big. Yeah. So we'll have those 5 problems you need to turn in next week. And those are problems that you don't need to write solution for, but you can look at them and we'll have, we will also post solutions. And for chapter 10, let's see how much we can get on Friday. We should be able to get a little bit. And we will probably post some corresponding homework problems and solutions so you can study for final. And for next Tuesday, let's we can it would be nice let's do a review too. Yeah. But yeah, so for final we're mostly on chapter 9 and well there are still chapter 5 and some chapter 10. Let's see how far we can get into. We are quite delayed also because of 端午节. So yeah, that's it. Any other questions about finals and last homework? If not, then is there any question about what we talked about last time? Now we dive very deep into all this pole zero analysis of our system function. Okay, and so this is a big thing about this chapter. Where is it? Yeah, this page. So we now learn to characterize your LTI system by looking at the RC of your system on the complex X-plane. And we find out that the system is stable if and only if your ROC contains your J omega axis. So kind of because it's stable if only if the Fourier transform actually exists. And and your system is causal. Let me make you yeah. So that's stable and it's causal. Not quite if only if this is a necessary condition. If it's causal, then then you must pick the ROC to be the most right-sided ROC. But the inverse is true only if the system is rational. So if your system is rational and your ROC is the most right-sided, then your system is causal. But we will just basically stay on rational. So, so that's that. So there are those 2 conditions. So stable means including J omega axis, and causal means picking the rightmost plane. And you can easily combine those 2 and say, do we have it somewhere? We should have. Yeah. And if you want to combine those 2 and say if you want your system to be stable and causal, then all your poles need to be on the left part. So you pick a rightmost ROC will contain the J omega axis. Any questions so far? If not, then let's see what we can say about systems by just knowing those two things. So first we go to this LTI system. And now it's a little weird. Okay, so we are still in the region where it's kind of similar to Fourier transform. So we can write our constant differential equation. We see that many times. And you do Laplace transform everywhere. Actually, called bilateral Laplace transform. We'll see because we call bilateral later because there is a unilateral Laplace transform. We'll talk about at the very end of the class. But anyway, so we have bilateral Laplace transform and new transform. And you can calculate your system function. It's very similar to how you do the Fourier transform. Basically, just swapping j omega to s. And you have those rational function here, h of s. And now when you do invert this thing, you can, now we know Laplace transform. When we do invert this thing, you can choose different RLC by thinking about what initial condition you are given. So this is already more general than what we do in Fourier transform. Because now we know the Fourier transform is basically picking the Laplace transform on geometric axis. And another way to say this is that okay, this is a little weird. But anyway, the thing we did when we do Laplace transform, when we do Fourier transform is we say the initial race condition, and as well as causal, and we basically always pick the RLC to the most right side. But now we can give different specifications. So maybe we will say the system is anti-causal, and we'll pick a different RLC. Okay, and then we look at this RLC thing again, and we solve for its system function. So before we'll solve this, and we can say input-output pair. But now we can look at the system function and see its rational function, and we do a little more analysis. We'll see that this is stable because all the poles have negative real part, and your RLC contains geometric axis, and it's causal. No, sorry, and it's stable. Yeah. Anyway, so that's a quick review. Any question? If not, then let's see more what we can play. Okay, so here is basically another type of question. It will ask you for this Laplace transform system function. So here is also, so this is the detective kind of question we are seeing now. So basically, you are trying to piece together all the clues and determine what your system function is. Okay. So yeah, the Laplace transform of your impulse response. So we start with I think this the second one is the most important one. So we start with the system is rational. So you know it's a polynomial divided by another polynomial, and we just told you that there are only two poles. And here it's a little bit unclear, but we mean two single poles. So single pole is -2 and 4, and yeah, you know the poles, so you already know the denominator, you can write it down. And the numerator is something you just say P of S. Okay, so that's some polynomial. And now we go through the other clues one by one to try to determine what is P of S. The end goal is we want to decide the system function. So the first one is the causal, and well, doesn't tell you too much. It tells you that yeah, sorry, it did tell you something. Okay, yeah. So Laplace transform, you need to pick the RLC. So the causal means that we need to pick the RLC that's the rightmost-sided RLC, and there are two poles here, one -2 and one at 4. So we are going to pick the RLC that's like to the right side of 4 part. Okay. Yeah. So we determine the ROC from the first condition, and then we need to use the other two conditions to determine this P of S. Now for this third condition, so if x of t equal to 1 and y of t equal to 0, so I think this is a little confusing, but this means that if your input function is this 1, so this is a constant function, then the output function is 0. Okay, so 1, 0. Okay, so and this condition is a little confusing because if you see this, you might. So this is a little digression. So if you see this, you might want to use the just Laplace transform everything. So big Y equal to big X times big H. And if you think about that, then you find out that the Laplace transform of a constant is actually not defined. So that's not quite doable. So we need to remember other thing about Laplace transform for the system function. So remember all the way, I guess at the beginning of the chapter, we said the Laplace transform is motivated as the eigenvalue of our eigenfunctions over our system is e to the st. Okay? And this x of t equal to 1 is actually in the form of e to the st. Okay? 1 is e to the 0 times t. Right? If you just pick s equal to 0. So so this is the eigenfunction of any LTI system, and then the output is the eigenvalue times the function. So yeah. So then and so from there we know the eigenvalue should be h of 0. Put h is equal to 0, and so we know h of 0 times this 1 should become 0. Then this h of 0 equal to 0. Okay, so h of 0 equal to 0, and the denominator is not 0. So you plug in s equal to 0 here, then you see that p of 0 should equal to 0. And so P must is one root at 0, so we say P equal to S times another polynomial. Okay. And finally, then this thing, the last condition, we have that the impulse response at 0 plus equal to 4. Okay. And so this looks really like the initial value theorem because it is 0 plus. And indeed, you use initial value theorem. So initial value theorem says the limit s go to infinity, this s times h of s equal to the initial value, which is 4. And s times h of s is s squared q of s, and divide by this s plus 2, s minus 4. And you multiply this out, and it's square minus 2s minus 8. But s goes to infinity, you only need to look at the highest order term. So it becomes s squared there, and this thing cannot have higher order s, otherwise it goes to infinity. So this q of s must equal to 4. Okay. And yeah, so it's a longer thing we say here, but anyway, it must be a constant, and k equal to 4. And yeah, so we determine our h of s, and we should also write the ROC. Then the ROC is s bigger than 4. Okay. Okay. So question. 再讲一次 P 等于 S equal to Q。OK， 这是因为 that's P of S equal to S times Q of S because P of 0 equal to 0, right? Alright, so H of 0 equal to 0, so then that must means P of 0 equal to 0. And yeah, so P is a polynomial that equal to 0 and 0, then you think about P in terms of all the roots, then roots of P, then P must have a root at 0, so yeah, so then P of S equals S times Q of S. Another way to say this is P of S. If you think about it as polynomial, write all the terms with different power. It must not have constant term, right? Because because P of 0 equal to constant term is 0, then everything has at least one factor base. Does that answer the question? Okay. Yeah. Okay, let me, where is my cursor? Okay, here. Yeah. Okay, so this is a problem that might or might not happen in your final. It's quite fun. Can do a detective work. Okay, then let's talk about a little more kind of application of all these analyses. Now we learn to construct filters. Okay, so a cool kind of filter is this called the Butterworth filter. It's a low-pass filter, and it has this parameter n here, and when n goes to infinity, it becomes more and more like an ideal low-pass filter, and the filter is defined in kind of this way. So we want its magnitude. So one is magnitude square to be 1 over 1 plus j omega over j omega c to the 2n. So the idea is that let's look at this picture. So there is a cutoff frequency omega c here, omega sub c here. So yeah, so every frequency less than omega c you want to pass, and bigger than omega c you want to suppress. And we do this by this omega over omega c. So if omega less than omega c, and then then this factor is less than 1, and you take it. So you think n is kind of a big number. So when n goes to infinity, is less than 1, and this is less than 1, and this factor goes to 0. Okay. And so this factor goes to 0, then you have 1 over 1 plus 0, so that's 1. And otherwise, there's a sharp transition when your omega goes to bigger than omega c. So omega bigger than omega c, and this is a number bigger than 1, and they will take infinite power, so this term becomes infinity. Then you have 1 over infinity, then becomes 0. And yeah, so this is when you plot those functions for different number of n, you can see as the angle become larger, the curve become more and more like your ideal filter, where you have a sharp transition and omega c. Okay, so that's the older Butterworth filter, and it's nice. And now we want to see, yeah, so we want to have this kind of magnitude, this kind of response in magnitude, and yeah, and we'll do our post-zero analysis to see how to construct things like this. Okay, and so yeah, let's start. So first, this thing is the absolute value of, what is it? Absolute value of some complex number. Then obviously it's bj omega times bj omega's complex conjugate. So nothing really happened. And now first we give a restriction of this filter. So we want to say the impulse response we want to be real, because yeah, most system, if a signal is real, then you probably want your impulse response to be real too. Okay. And then you and yeah, if you restrict that, then the Fourier transform property just tells you that this conjugate equal to b to the minus omega. Okay. So yeah, so you plug this in, and you back to, so all those three together, then you back to bj omega times b to the minus j omega equal to, or whatever on this side. And then we do a little weird thing. So we I think this is actually not unique thing you can do, but anyway, but this is how we do it. So we want to satisfy this. Okay, then we satisfy this thing by trying to construct some B of S. And we see that we can satisfy this if we have some B of S such that B of S equal to, so basically we swap J omega to S. So B of S times B of minus S equal to 1 over this 1 over S over J omega to the 2n. Okay, so yeah, basically swap J omega to S. Then if B of S satisfies this equation, then B of J omega will satisfy this equation. That works, right? But I want to say a little here, this is not the only B of S that can satisfy this, but this works, so we pick this. Okay. Anyway, so yeah, we swap J omega to S, and we can satisfy this equation by solving for something that satisfies this equation. Okay. Now we try to solve this equation by trying to find the poles and zeros of this B of S. Actually, they're only poles. Anyway, so I want to try to find the poles of B of S. But first, let's find the poles of this B of S times B of negative S. So this part. So what are the poles of this thing? Well, it's still a polynomial. It's a polynomial to 2n power, so it's to the 2n. But anyway, you can solve what's 1 plus s over j omega c to the 2n equal to 0. What's that? Then that's s over j omega c to the 2n equal to minus 1, and you take 2n's root and move things around. Then it should be the poles of this thing should be at s equal to minus 1 to 2n's root and times j omega c. Okay. And now that's just standard complex calculation. And yeah, so you will have, and so solution for those things we call it SP. So solution for this we call it SP, and obviously, so this is like 2n's root of minus 1, and j is also a phase. So all those things are phase, and omega c is the real number. So the magnitude is just omega c, because everything other than omega c is just a phase. And yeah, so they are going to be, those roots are going to be on a circle with the radius omega c, and then you can easily solve the angle. So the angle is going to be, so this is j going to give you pi over 2, and this is negative 1 to a 2n's root is going to be, well, negative 1 is like 2k plus 1 pi and divided by 2n. Okay. And if you put things together, then you have the the absolute value is omega c, and your angle exponential j, and all this pi over 2 and then pi 2k plus 1 over 2n. And yeah, so you can plot this for different n. Okay, so then go for different n. So you can see n equal to 1, there are 2 roots, and because it divided by 2n is 2, so there are 2 roots. And n equal to 2, there are 4 roots, and n equals 3, there are 6 roots, and n equal to 6, there are 12 roots. And you can see there are always symmetry, so it's going to always be symmetric left and right. And the number of roots is 2n. Okay. And yeah. And so we have some things you can say about roots. So obviously the 2n, actually the poles. So the poles are equally spaced around this circle, because yeah, the circle of radius omega c, and they are equally spaced because the spacing comes from this -1 to -1 to the 1/2n. Okay, so the spacing or is pi over n, so 2 pi divided by 2n, and from this thing you can easily prove something, and yeah, from this you can, well, let's skip it out, but you can say it's a left-right symmetric, and also how you place those things. The pole will never be placed on the imaginary axis, and if n is odd, then there will be poles on the real axis, and if n is even, you will not place on the real axis. You can verify those from those equations, and let's skip that. And anyway, so that's what the poles look like. They are something on a circle. And what we really want to know is, so they are actually poles of B of S times B to the minus S. And what we want to find are the poles of B of S. Okay. So what are the poles of B of S? Oh, also, I guess then we also see that these things don't have zeros. Okay, so we just want to find the poles of B of S, not zeros of B of. There will be no zeros of B of S. But anyway, so we will pose of B of S and times B of minus S, and so now for whatever function B of S it is, we see that the pose of B of S times B of minus S must occur in pairs, right? Because this thing is symmetric when you take S to negative S. So whenever you have a pole at S, then it must also have a pole at negative S, right? Because B of S is a pole at S, then B of negative S is a pole at negative S, negative SP, right? Yeah, so that's good because you see the poles here are also in this S negative S pairs, right? So basically we just need to assign, so for those pairs, so for example, in n equal to 1 you have 1 pair, n equal to 2 you have 2 pair. So basically, and again, n equal to 3 you have 3 pairs. So basically for each of these pairs you need to assign which pole belongs to B of S, and which pole belong to B of negative S. And now we put, and that's kind of arbitrary. You can construct many filters. But now we do more condition, that is we want our B of S to be stable in the causal, because that's a better system to construct in a actual physical way. And so we want the pole, and just from the beginning of the class, we know that if the system is stable in the causal, then all the poles must stay on the left side plane. So all those pairs, we want B of S to pick the left side part, and B of negative S to pick the right side part. Yeah. So yeah, so now we know the B of S is poles of those things, and there's no zeros, and want it to be also a rational function. And the only thing, so we basically know B of S, and the only thing left is there might be a scaling factor. Yeah, we know the positive location, and there might be a scale factor. And we can just check an earlier equation and say this one. And and we plug into S equal to 0, and we see that B of S equal B of 0 times B of 0 equal to 1. So B of 0 should equal to 1. Oh, I guess it can be -1. That's a little weird. Yeah, so B of S squared equal to 1, and when S equal to 0. So B of 0 is basically plus -1. And yeah, but I think Yeah, I think it's better to pick B of S equal to +1. So let's see some example. So yeah, so we have an example for n equal to 1, n equal to 2, n equal to 3. And so the poles of B of S, as we say, will be a left side pole of on the circle. So 1 is this pole, and for 2 is those 2 poles, and for 3 is these 3 poles. And if you write down the number, then B of S equal to this thing. Okay? Once again, we have SP equal to this, and yeah, it's like multiply all the. So we had divide by omega c, but we multiply by omega c. But anyway, that's the B of S. And n equal to 2, we can also write down the B of S like this, and n equal to 3. So yeah, you see the second order equation here, second order polynomial here, and the third order polynomial here. And yeah, so so now we know the system function of our filter, and finally, finishing the construction of our filter. We can construct the differential equation. I guess we'll see a little more of this later. But now we can write down the differential equation of our filter. Okay, so this will also be nice for how you design your filter, because you probably want, say, an electrical circuit that will give you the system function, and first step to do that is write down a differential equation corresponding to the system function. And well, if we do this in the other direction, so we had a differential equation can write down system function. If a system function is also very easy to write down differential equation. Basically, you just see the coefficient here and then put in the coefficient here. Right. So yeah, so those are the differential equation of your system function, and like the first two are the first order function and the second order function we talked about a little bit about on this chapter, and obviously there will be a third order function. And I think later part of this chapter we'll see how to construct those kind of things from blocks of system elements. Okay. So any question about this construction of our Butterworth low-pass filter? So yeah, we derive how to construct a filter that look like this. And you can see, well, higher order filter has like sharper transition around your boundary, but also it requires higher order differential equation, and you can probably guess that this will require a more complicated circuit to construct. So that's kind of a trade-off. Okay. 15 minutes. Okay, let's see how far I can go. And I can probably finish this. Okay. Then let's talk a little more about those pole zero things. And the first is we want to talk about OPACE system. And well, we introduced the OPACE system a little before, but let's do a review. So I think I made a little mistake before, but so OPACE system is a stable system, and so the important thing here is that the magnitude is constant. Before we said the magnitude is 1, but definition is actually constant is right. Although anyway, yeah. So the magnitude is constant, and constant is independent of frequency, and that's the OPACE phase system. But it's a little more than just being 1 or constant, because the phase can still depend on your frequency. Okay. So that's open system, and if you want to write down this in equation, then that's like a system function is going to have a constant magnitude, and then you can have some phase that depend on the j omega, depend on omega. And now if you, okay, so let's thinking about the Fourier transform. Now if you think about Laplace transform, is hosting the S-plane, and you want it to stay constant on the j omega axis. And if you want it to also be a rational function, then as before, we think about how the magnitude of this thing will change when you switch around, and it depends on distance with the poles and zeros, right? And so this is a necessary condition, but so this is a sufficient condition, but I think it's also necessary. So we'll skip the proof that this is necessary. But you see that if the pole and zeros all have this symmetric pair, so whenever you have zero, so you have a pole at AK, then and you also have a zero at AK star, then you move around the zero omega axis, then you look at your distance to AK is same as the distance to AK star, so this will also always be 1. Okay, so this distance divided distance will always be 1, and it will stay constant magnitude when you move around its omega axis, and you will get some vector depending on the angle. So you see that if H has this form, so your pole and zero has pairs and times some constant A here, then this thing will have constant magnitude because this side has magnitude 1 always. And so this is sufficient, and I think you can prove that it is necessary, which we will now prove here. So that's open system. And yeah, that's what we say. And if we add a little more constraint that we want the real open system, so want the impulse response to be real, then for yeah, for real signal, its Laplace transform need to satisfy this equation: x star of s equal to x of s star. Okay. And now I draw a picture. So so because it's an open system, so we start with a pole here, then it must have a 0 here. Okay. So this is because open, so you have this pair. Then now you also need to be real. So when you take complex conjugate, so you go to x star. So this is s star, so it will go from this point to this point. This is doing complex conjugate. You swap the sign of the imaginary coordinate. So you go from here to here, and well, then you go from infinity to conjugate of infinity. But conjugate of infinity is still infinity, so you should also have a pole here. And then here, you go from here to here, then you go from 0 and the conjugate of 0, which is also 0. Okay. So you must have a pole. You must also have a pole here and a 0 here. Okay. So yeah, so a real open system. When you got a pole here, then you must have 2 0 here and another pole here. You always have these 4 things together. Any question? Well, there are special cases where there are not 4 things. So if you happen to be on a real axis, then there's no up down pair. So you will still have this left right pair. So yeah, so that's what the pole-zero plot of open system will look like. You have some, well, yeah, you have some poles and some zeros, but we want to be Koso stable, then we want the poles on the left hand side and the zeros on the right hand side. Any question about this pole zero plot for opaque system? If not, then let's look at the other thing. And the other thing is the amino phase system. And well, it's something that so the idea is we want the inverse to be causal stable. So we want the system that's causal stable, and its inverse is also causal stable. And if thinking about this, then it means all the poles and zeros must be on the left plane. So that's because we start with this causal stable. So all the poles must be on the left plane. And when you do an inverse of a system, and we think just think about its original system. If you do an inverse of a system, then the inverse will have big H become 1 over big H, and it will swap all the poles and zeros, so 0 become pole, point become 0. So then all those zeros should also stay on the left hand, should also be on the left hand side, so the inverse will also be causal and stable. So yeah, so that's the minimal phase system. It's something that has its poles and zeros or on the left hand plane, well, all the finite zeros. Yeah. Any question? Yeah, we say finite zero because it might have 0 at infinity. That's okay. And and then yeah, let's see the example of a system that's actually not minimal phase. Yeah. So yeah, it's a rational function, and we will do the factorization. So it has 0 at 1, 0 at -2, and poles at -3, poles at -4. So this is actually not a minimal phase system because you see there's a 0 at this right hand side. But now we do something funny. We decompose this into a minimal phase system times an opaque system. And so what we do is, okay, so this okay, how do I say? Okay. So the thing is, so this 0 and 1 is a little annoying. So what we do is we construct the pole zero pair at -1. So in terms of equation is we multiply our system function with this s plus 1 divided by s plus 1. So nothing happens because this thing is 1. But then we can swap things around, right? So we swap this s minus 1 with this s plus 1. Okay. And now this side has s plus 1, and this side has s minus 1 over s plus 1. But now, if you kind of separate those two things and think about their property, and now this is a minimal phase system because, well, it's always plus something, and means all the 0 and poles are on the left hand side. You see 1, 2, 3, 4. And but we are multiplying it with the extra factor. But the extra factor is s minus 1 over s minus 1 over s plus 1. And this thing has 0 at 1 because inherited from 0 at 1 at the very beginning. And also at the pole at -1. But yeah, so it has this symmetric pole zero pair, and it's an opaque system. And so here is an example that you can always decompose your system into a minimal phase system and an opaque system. And it's pretty cool, and you study more, you will have applications in analyzing your system, but we will not delve into too much detail about that. Okay. Any question on this decomposing of system into minimal phase and opaque system? Not, we have 3 minutes. We can probably not finish this, but let's look into it a little bit. So yeah, so we can, so we go back to the thing we do to the Butterworth system, Butterworth filter. So whenever we have a transfer function, if we know the magnitude of a transfer function, so if we know the magnitude of h of s or h of j omega, something, and we show how to construct the h of s that will give you the required magnitude of h j omega, and that when that is h of s, that's stable, real, and causal. So it's a nice thing to construct the actual physical system. Okay. And it starts with really like what we do with the Butterworth filter. So we say h of j omega obviously equal to h omega h complex conjugate of j omega, and then we use the condition that our impulse response is real. So this star becomes negative sign inside, and so yeah, so this is h omega h minus j omega. Then we try to satisfy this by using this thing equal to hs times h minus negative s. Okay. And it is equal to j omega. And then you can analyze the poles and the zeros of hs times h negative s. So basically, this thing will going to be we'll think about it as a rational function, and whenever a factor of whenever h of s has a factor s minus a, then h of minus s must obviously has a factor s minus s minus a, and so this thing will be factor of minus s plus a squared. And because of the symmetry, the poles and zeros will have all kinds of mirrors. And but we're out of time, and we'll finish our spatial factorization next time. So any question? If not, yeah, then see you on Friday.